Alright, this is a lesson from Chapter 10, 10.1. As we begin Chapter 10, we are moving towards the notion of integrals in calculus. And one of the things that integrals does is it shows us areas underneath curves. And so that's what we want to focus on first here. We're not talking about an integral yet. But what we're talking about is how to calculate using antiderivatives, how to calculate areas under curves. And I'm going to start with some simple examples. And I'm just going to kind of show you the development of how we move towards integration and things like that. So what I want to start with here, and this really, from the textbook that we're using, the Red Stewart, this is 10.1. What I want to first of all mention is that this shape of diagram here, this shape right here, is called a trapezoid. And I won't go through in this video, how this area formula comes about. But a trapezoid has two sides that are parallel to each other, and the area for a trapezoid is 1/2 A, which is the length of the one parallel side, plus B, the length of the other parallel side, times H. So this is the area for a trapezoid. And over here on the left, I've got a line, and this is y equals x plus 1. And if I ask you to find for me the area underneath this line, x plus 1, and above the x-axis here, and from 0 to 1, that shape of that area is a trapezoid. See that? It's the same as this over here, it just flipped onto its side. So if I wanted to calculate this area, I could easily do that. And note that I have a grid behind here. And so we could honestly just count the squares, right? This is 1.5 squares. The area is 1.5. How could we use the trapezoid formula? Because we're not going to just be able to count squares on a grid paper. So how could we do that? Well, if we think about this area as a trapezoid, the area here is 1/2. Now A plus B, so A is this side right here, which is 1. B is this side, which is 2. See that? So that's 1 plus 2. And then times the height, which is this length right here. You see, height here. This length, which is 1 unit for height. So if we do that, 1/2 times 3 times 1, half times 3 is 1.5 times 1. So that's how we can calculate that, right? So that's our first example. I am going to move quickly to a second example where the trapezoid, it looks a little bit funny. It's still a trapezoid, but we have an area that instead of spanning from 0 to 1 here, we're going to span from 0 to 4. All right? This side is still 1. This side is now 5. Okay, and this side, of course, is 4. So the area here is 1/2 times 1 plus 5 times 4, which is, that's 1/2 of 6 is 3 times 4 is 12. And let's see if that matches up here. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 whole, and then another 2 halves is 11, and another 2 halves is 12. So that's 12 square units there. The third example I'm going to show you here is this one. Now I want you to notice that the area that we see here, okay, the area that is enclosed here, another trapezoid, and I'm just going to quickly count the area instead of doing the formula. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.5. Okay, so the area is 10.5 units. Now if you notice a couple things, that area is the difference between this larger area and this smaller trapezoid area. So I've taken this smaller area off the larger. And do you see how 12 units is the large area and 1.5 units is the smaller area? And so that makes sense, right? If you have two areas and you want to find the difference in those areas, you subtract them. And so really this is 12 minus 1.5 is 10.5. Okay? So from there, okay, so that's, first of all, I want to just reiterate a couple things here. Trapezoid, all right, if we use a straight line and we use the axes, x and y, and a straight line, we can form a trapezoid. And we could pretty easily, with non-calculus methods, find the area of the trapezoid. All right, what I want to do now is I want to do another example here where we don't have all these numbers. And I want to do something a little more general where, and let's go back actually to this one here. This is what I want to do. Okay, so I want to go back all the way to 0. Okay, and I want to use this kind of large area. Oops, I don't want to get rid of that actually. So let's get rid of this part. And so let's say instead of this being 4 and this being 5, let's say we don't know what these are, but we're going to label them as, this is going to be x here. Okay, and of course the height here is going to be x plus 1. You see that? Because that's the equation of the line. So we have 0 here, and of course this is 0 plus 1, or 1 right here. So what's the area of this trapezoid where I don't really know what the endpoint is, but I'm just kind of coming up with an expression? Well, 1/2, okay, and what's a plus b? Well, that's going to be 1 plus x plus 1. And the height is going to be x minus 0, or x. So what this is going to do is this is going to give us an expression for the area, right? So that's going to be 1/2, and that's going to be 2 plus x times x, or 1/2 of x squared plus 2x, or 1/2 x squared plus 1x. Okay? Now, it doesn't matter what this distance is, as long as it's x. So this, could be another x here. We're going to have the same expression for the area. You see that? No matter what size of trapezoid you have. What I want you to do is I want you to focus on this expression for the area. Okay? And I want you to look at this versus the expression for, or the equation of the line. Now, I asked my class this earlier. I said, how are these related right here? And it took a little while, okay? But eventually, with some hints, we came up with the fact that this right here, okay, if I did this, plus c at the end, they started to recognize what this was. And this here is an expression for the antiderivative of this. Isn't that neat, eh? The line, which is the upper boundary here, right? The equation for the line, okay, is the derivative of the general expression, right, for the area underneath that curve between that line and the x-axis. So that's very interesting, and that is very important, okay, that we can actually use this. Now, how does it work? I wonder if I use this this expression here. If I plug in 1, I should get an area of 1.5, right? So if the area equals 1/2 x squared plus x, right? That's what we have here. Don't worry about the c for now. Okay, don't worry about the c. But if I plug in 1 into this function, really, I have 1/2 1 squared plus 1, which is 0.5 plus 1, or 1.5. That seems to work, doesn't it? And if this right here, I kind of stole this diagram, so let's change this now to 4. So we've got 4 here. If this x value is 4, I should have a of 4 equals 1/2. And stick with me here, I am making a point. Okay, what is this? Well, 4 squared is 16, half of that is 8, plus 4 is 12. And of course, that is what we figured out this area to be right here, 12 units squared. So this definitely is an expression for the area of what would be this shape underneath the graph and above the x-axis. Now, it is only going back to 0 here, but it's useful for any value of x. Okay? So what I'm saying is that there is a relationship between the equation of this line, that would be the upper boundary of the trapezoid, and the area under the trapezoid above the x-axis from 0 to x. Okay? Very important. There is a relationship there. I'm going to come back to this one right here, okay? But there is now. I'm going to get to this here in a second. Ooh, I'm not sure what you did. So let's do this now, I guess. This one right here. How do I find this area? Well, if I know the area, for if this was 4 and this was 1, I know how to find the area for 4 and I know how to find the area for 1. So if I want to find this area, I'm going to subtract the area up to 4, back to 0, and the area up from 1 back to 0. I'm going to subtract them. So I'm going to basically do this. The area up to 4 is going to be, okay, from 0 to 4, is going to be the area all the way up to 4 minus, no, this is a bit misleading here, sorry. Let's just put this, I'll just say area here. Okay, this is coming later. So area, okay, of this right here, is the area all the way from 0 to 4 minus the area from 0 to 1, right? And that gives us our 10.5 units. So the area underneath this graph can be determined when we do this sort of subtraction here. And that leads us to sort of a general statement about finding area under a curve. So let me just show you this. What I mentioned in class here was that the derivative of the area function, okay, and the upper boundary equation are related. We saw that, right? And I worded that as being the upper boundary and the area function. The area function is the antiderivative. So if we say the derivative of the area is the upper boundary equation, we can use that to find the area under the line. And I do want to make note here that I've written area under a curve, okay, because, and this is really, really cool, that it is in fact true that the area underneath this line and above the x-axis from A to B can be written like this. This is the sort of the point of this lesson right here. But the interesting thing is that this function, whether it's a line or a curve, the same truth holds true here. So really, I'm going to just sketch this out. And if this wasn't a line, if this was some sort of function like this, you know what? We can use the exact same idea here. Because this is just f of x, I can find the antiderivative of this curved function, and I can use the antiderivative to find the area underneath this curved boundary area. And that is huge. That's very, very important. It doesn't have to be a straight line, and certainly this is not a trapezoid, right? But if you think about it, and I won't get into it in this lesson here about limits, but if you take a peek here, we could separate this into a whole bunch of smaller sort of trapezoids, right? That is going to be very close. If we add up all of the areas for these, you know what I'm saying? Add up all these little areas of these little trapezoids, that's going to be very, very close to that area underneath this curve, right? And so, really, this is sort of like a limit of all of these sort of defined trapezoidal functions, and that's another concept in calculus we're not going to deal with here. But the antiderivative and the area underneath the curve, this is how you do it, this is how you use it. And just check out my other videos for an example. I do this example on another video on how to find the area underneath this curve here from 2 to 4. And you simply do that. So I'll let you look at this for a little bit here if you don't want to watch that other video, but I go through this equation in my other video. I believe that's called Calculus 30 10.1 area under the curve example. So hope you learned something, and have a great day.